Thank you for the invitation. Thanks to the organizers for the opportunity to speak here today. I wish I could have been in Montreal. Unfortunately, some things happened. I couldn't come in person, but I'm glad I'm able to give this talk remotely. So what I wanted to talk about today is something that I got into a couple of years ago because of a discovery that was posted. So I'll talk a little bit more about that. But in general, I work in association schemes and I'm really interested in constructions. And one of the things I've been wanting to do more is to look at things which have smaller and smaller kind of symmetry assumptions on them. A lot of times to build things, you try to use some kind of group or something to do that. And of course, if the group's too big and you ask too much of it, then you end up with something that's been classified. And so you want to pare down and get to some kind of weaker symmetry assumptions that give you something feasible and a chance to find something new. I don't know if anybody, I can't remember if anybody's talked about conference. I know Hadamard matrices have come up. So a conference matrix is very similar to a real Hadamard matrix. You just want an n by n matrix with zeros on the diagonal and plus minus ones off the diagonal. And the matrix times its transpose is n minus 1 times the identity matrix. And here is two smallest examples. And they're kind of prototypical examples in the sense that you'll notice the one of order 4 is skew symmetric and the one of order 6 is symmetric. And while conference matrices don't have to be that way, they do have to be in some sense equivalent to something like that. One thing you can do in a conference matrix is you can multiply rows by -1s, you can multiply columns by -1s, and you can swap columns and rows in the same way to preserve zeros on the diagonal. And all those sorts of things, those are equivalent. And it turns out that really for conference matrices, they come in those two different flavors. So these were defined back in 1950. And this was actually originally for telephone conference calls, but like association schemes in general, it's the sort of thing that can come up in different ways. And so is an interesting idea beyond its original application. So this theorem, which I think goes actually back to Belovich, so is an exercise in Van Linton Wilson's combinatorics book, is that when you have conference matrices of order n, n is even, and if it's congruent to 0 mod 4, it's skew symmetric, and if it's congruent to 2 mod 4, it must be equivalent to a symmetric conference matrix. But also you pick up an extra condition that n minus 1 has to be a sum of 2 squares. This condition is particularly interesting to me because this is a condition that also comes up in some design theory questions, and it kind of confounds some people's intuition in design theory, where they think maybe if everything's big enough, obvious conditions are sufficient. And this, I wouldn't exactly call this an obvious condition. We're going to focus on the symmetric case. Where does that sum of 2 squares condition come from? Is really just rational quadratic forms. And Minkowski solved the question of congruent rational quadratic forms. And Van Linton Seidel gave in a paper a clever proof of this, also without using these kinds of invariants that Minkowski came from. It's kind of nice, though, to know that there's this general theory going on in the background, too, of this idea that if two matrices are congruent when there are these matrices on either side, and really a conference matrix is saying the identity is congruent to a multiple of itself as a quadratic form. And there are invariants that tell you whether that's possible with a rational matrix. Now, my own personal the reason that my eyebrows kind of raise when I look at that condition, though I've been afraid to really do anything with conference matrices for a while, is that I'm really interested in the question about projective planes and if non-prime power order projective planes can exist. And there's a similar condition. And, whenever I talk to someone maybe who's not familiar with projective planes, they always say something like, well, if n's big enough, they probably all just exist. And then I bring up this condition. And then the temptation they always have is to say, well, maybe if things are big enough and n's the sum of 2 squares, then they exist. And I don't know. I don't know how to feel about that because this condition isn't so combinatorial as like a simple divisibility or something like that. So it kind of, but I'm really curious about projective planes. Now, conference matrices are kind of interesting. There's been no order of a conference matrix that's feasible where it's been proved that there's non-existence. So now there is an order of projective planes where there's proved to be non-existence. So is it possible, though, in conference matrices that this really is the only barrier to things existing? And that would be kind of interesting to me to know that that could be really the only barrier for something. So that's one reason why I'm interested in this particular problem. Now, conference matrices, though, and really have a close connection to association schemes in that from these symmetric conference matrices in particular, you get strongly regular graphs. You basically normalize it again by multiplying by plus and minus ones. So you have ones here, one here. And if it's symmetric, you can do that. So this is a symmetric matrix. And it's ones and negative ones. So you can just, with zeros on the diagonal, so you can write it as the adjacency matrix of a graph minus its complement. Okay, so what is this graph here? What does that have to look like? So it has to be, and I think strongly regular graphs have been talked about enough that I can actually talk about a strongly regular graph here. Has to be a particular kind of strongly regular graph, which is sometimes called the half case. The parameters are, well, the valency is exactly half, and the parameters are self-complementary in that the complement of a strongly regular graph is always a strongly regular graph, but the parameters may be different. In this case, they're exactly the same parameters. That doesn't mean they're isomorphic to their complements. They may or may not be, but they have the same parameters. Okay, so when you have a conference matrix that's symmetric, that's really equivalent to the existence. So it's really equivalent to the existence of some kind of strongly regular graph. Now, this strongly regular graph set is interesting because it's the only case of strongly regular graphs where irrational eigenvalues come up. All the other strongly regular graphs have integral eigenvalues. And since these are all integral matrices, when you look at certain things, actually it gives you a little more information and a little less guesswork on characteristic polynomials. So this is and it also a particularly interesting case for strongly regular graphs, but it's also kind of a scary case because a lot of the tricks you'd want to use to kind of prove that a strongly regular graph maybe doesn't exist or something, it's hard to do here because the valencies are as big as they can possibly be. And the eigenvalue multiplicities are as big as they can possibly be. And, you know, some ways that some strongly regular graphs are dealt with is, well, if some parameter is small or some multiplicity is small, so you have some small dimension representation, you can do something. Well, you know, everything here is as big as it can possibly be. Now, one infinite family of conference graphs known comes from the Paleographs, which go all the way back to 1933. And these are just from finite fields, basically finite fields congruent to 1 mod 4, and you connect them if their difference is a non-zero square in FQ. It's easy to show these are indeed conference matrices. And that's an infinite family right here, just that's only for Q being a prime power. And again, this is another thing that comes up when you're working with projective planes. So, you know, that's another reason why I find it interesting. Here are the known orders of conference graphs, and the situation here is different than that of projective planes in that non-prime power examples of conference graphs are known. And by the way, Q here, I'm just always going to have represent the size of the adjacency matrix of the conference graph. So it's not the size of the conference matrix, just a conference graph. And we're just henceforth going to just talk about conference graphs. Okay, so what are the known examples? So Jennifer Seabury and Whitman had some survey paper. They had lots of constructions listed, and they come from, well, there's the Paleograph. Seabury and Turin said, well, okay, if you can find a conference matrix, you can raise, I did have to phrase in these slides some in terms of conference matrices to get the numbers to work out right. So yeah, I think this is a typo here. I think yeah, we might have to fiddle with that a little. No, actually, I think these are, I think what's actually going on here, these are powers. You can take the power of a conference graph. And then, yeah, there are these plus ones that should be added on to there. And that's where I messed up. And then let's see, this particular one is due to Rudy Mathan, and this gets you the one of order 45. So you have p squared and p plus 2. So 9 times 3 plus 2, you end up with 45, and that gives you the smallest feasible case, not of a conference matrix, but of a conference graph. And then there's a particular construction of Seabury. But the whole point is not many orders are known, and some of these cases are recursive, so you actually need smaller conference graphs to make bigger ones. Okay, so a lot of orders really aren't known. Now, for a long time, the smallest case of parameters for a strongly regular graph where it wasn't known whether it existed or not was on 65 vertices. And it was exactly one of these conference graphs. And one day I was preparing a talk just for my local seminar to talk about strongly regular graphs, and I looked at the table, and there was this entry where it just said that this was found and that the name Gritsenko was there. And I couldn't find any paper or anything. So I wrote to Andries Brouwer, and he sent me a very short email just saying, Gritsenko sent me the following matrix. And actually, let's see, Bill made this picture of it. This isn't what Andries sent me, but Bill made this picture of it using apples instead of ones. And so this, basically though, this is all the data you have. You have this big matrix here. And that was all Gritsenko at that time has sent him. So, you know, there was this fascinating question, just how did he do it? And regardless of how he did it, how can this be generalized? So for a few months, I had no idea how this was done. It was not actually until February, I think, yeah, from October to February, that he actually posted a paper talking about how he did it. And he did it by looking for ways to knit together circulant matrices and then using some clever specializations. It's a big search space, so using some clever specializations to find some solutions. All right, but in that interim time, there was some time to think about, well, you know, how could this graph be generalized and take a guess as to how we did it, though it turns out the direction we ended up was somewhat different. I just have a matrix, want to generalize it. You know, well, how do you build new strongly regular graphs in general? Usually you try to make some kind of symmetry assumption. It's not the only way that things happen, but, you know, just in general, compact, controllable way to construct something, a group is a big go-to thing. Just assume some kind of symmetry on it. And like one quote I liked, Tim Pentilla likes to say that groups are the suitcases we carry our constructions around. And so, you know, that if you can make a group assumption, it can make your life a lot easier. Now, if you make too big of an assumption, like the graph is vertex and edge transitive, then you end up with classifications of rank 3 groups and things like that, you know. So you need your symmetry assumption to be, needs to be strong enough so you can do something exhaustive. And that's really what I wanted to do. I wanted to hedge my bets a little and do something exhaustive. but at the same time weak enough that it doesn't just follow from some other kind of classification or doesn't give enough chance for things to exist. In general, symmetry assumptions lead to group theory descriptions because, the orbit stabilizer theorem, really what's going on there is that it's saying all these things that you think groups act on, groups don't act on anything except themselves. And when you see some other action, it's really the group acting on itself in some way. Cosets of subgroups, some multi-set of subgroups. That's really all the group actions the group ever does. So you can usually just take your symmetry assumption and turn it into a statement about, well, I'm looking inside the group for something. And like, for example, I use the word sharply transitive. Some people use the word regular. Just the stabilizer is trivial. So transitive, but the stabilizer is trivial. If you assume that on a graph, for example, then what you find out, you can identify the vertices of the graph with a group. And let's see, the previous speaker mentioned Gotzel and Royal's book. You can see a description of a lot of that in their book. This leads to, I'm now searching for some kind of subset of a group. In this case, you can search for some connection set, C, that's inverse closed. And if you want a graph which has a sharply transitive group acting on its vertices, you can describe it now just by a subset of the group. Those are the neighbors of the identity, and the group is just pushing that around. So that's your whole graph is now just stored in that connection set. And all you have to do is look for the connection set. And Paley graphs are an example of Cayley graphs. I mean, you have the additive group of the field acting on them, and you end up with this same kind of equation that was at the bottom of the last slide. My apologies to people who put the inverse on the other side. I like to act on the right for automorphisms. But, okay, so that's one symmetry assumption that probably everybody here's seen. So what's going on with the graph that Gritsenko found? So that one was not vertex transitive. What was really happening is so this had 65 vertices, and it had an automorphism group of order 32. So you have a fixed vertex. It has 32 neighbors, because again, the valency was pretty much half the graph. And then it has 32 non-neighbors that are all at distance 2. So you've got these 3 pieces that we often call subconstituents. And the group was acting sharply transitively on each subconstituent simultaneously. So, and that was it. There's no more symmetries. That's just this group of order 32 fixing one point and basically giving you a Cayley graph on each subconstituent that are knitted together. And the group itself, actually, interestingly, was non-abelian too. A lot of times in constructions, people prefer to use abelian groups. Things work out more nicely, and the representation theory is nicer too. But this was a non-abelian group. It's actually a non-abelian group, and it's also a non-split extension. So it's not, I can't write it as a semi-direct product. But it did have this big abelian group in it, this big cyclic group of order 16 inside it. So like half the group is an abelian group. It doesn't have a big center, but it has a big abelian group of index 2. I list it here as G20. If you use any group databases, both GAP and Magma have it as the 20th group of order 32. So the idea then, when looking at that symmetry group, the idea was to generalize from that. So henceforth, we just assume that we have a symmetry group that fixes a point and is sharply transitive on the neighbors and sharply transitive on the non-neighbors. And so now we end up with 3 connection sets. Basically, S1 and S3, those are in the different subconstituents, and those are inverse closed, like Cayley graphs. And then we have one going across, which is not inverse closed. And in general is the bottleneck for searching for these sorts of. Okay, so the Paley graph itself, and let's see, oh no, this is just a general description again. Yeah, so if you want a vertex description, basically I have vertices grouped by the fixed point, then the first subconstituent and the second, and again they're all indexed by elements of my group, in this case A. And well, adjacency is defined similar to that of a Cayley graph. And so again, acting on the right, you get these automorphisms from that. So in order for this to work out to get a strongly regular graph with the right parameters, what you end up having to look at is these particular intersection sizes between the connection sets. And those are just explicitly looking at the parameters. Okay. And here, instead of Q, I wrote it as 4t plus 1. It's just a little easier. So this is what you have to check. This is what your connection sets have to do for this to work. So yeah, for example, this was what you would need to find an example like Gritsenko found. Now now you might think, well, this could be a fluke, but actually, I mean, the Paley graph itself is constructed in this manner. If you stabilize, say, 0 in the finite field, you can multiply by all the squares in the field, and those are automorphisms. And so you do have, in this case, cyclic groups that are constructing the Paley graph. So you can recover the Paley graphs like that from this. So actually, a lot of examples known are from this construction, if you look at it this way. But also, you can get things non-isomorphic to Paley. So the smallest one that you can find, because Paley graphs are unique until you get to 25. Paley graphs are the unique conference graphs until 25 vertices. But for example, on 25 vertices, instead of a cyclic group, you can use this group here, which is also abelian. Take different connection sets, and you get a conference graph that's not isomorphic to a Paley graph. There are also non-abelian groups here that you can get things from as well. But I just wanted to give a simple example of something that's not Paley. And by the way, I haven't really talked about two-graph switching, and I wasn't going to talk about it a lot, but you know, this is not two-graph switching equivalent to the Paley graph, because you just get Paley graphs back when you do that. So this is something different. Now, oops, yeah, this caption shouldn't be Paley graphs, but down here, if the group assumed is abelian, actually it turns out there's only really one condition that has to be checked, and the rest comes for free. So it's particularly nice if you can use abelian groups to do this. But the interesting thing was that Gritsenko's example from this construction comes from a non-abelian group. So I don't want to restrict to just abelian groups. So for non-abelian groups, it's a little bit more complicated. There was some redundancy in what I'd written down. You have to check this condition about how S1 and S2 interact. And then if S2 has this property here, then actually you can just take S3 to basically be the complement of S1, and it works. And that works for the Paley graphs, it works for Gritsenko's example. And so it's a lot nicer, because then you don't have to deal with 3 connection sets. You really only have to deal with 2 and a smaller condition on the second one. This doesn't mean things commute with S2, but somehow the intersection sizes are the same when you multiply by on either side. Getting these kinds of conditions, by the way, if you sit down and play with them a little, you know, at some point, I took some inverses and multiplied by things just to make it easier, but it's pretty straightforward to get to these conditions. So now one thing, though, that narrowed the search space a lot was also noting one thing about involutions, just a very simple thing, that anytime you take a subset of a group and you push it by an involution, the intersection of this must be even. Now, the lambda and mu of these strongly regular graphs have different parities. So that actually tells us something, that S1 has to contain all the involutions if Q is congruent to 1 mod 8. And S3 instead contains all the involutions, and S3 doesn't if Q is congruent to 5 mod A. So the upshot is if a group has a lot of involutions, actually, then because they all have to be in the same place, a lot of times that just means it doesn't work. In particular, it's very easy to see the dihedral group is never going to work here. There's too many involutions in it. But sometimes also you get other examples where there's just too many involutions and they're not going to work. Now, that rules out some things, but there's plenty of groups that have a single involution or something like that. So we also have interlacing on our side to do some things with. So these graphs, we know what their eigenvalues are, and we know that any subgraph has to, that any induced subgraph has to interlace the eigenvalues of the putative big subgraph. And we also, so that's just the standard interlacing statement. And we also have equitable partitions on our side, because anytime you have one of these kind of Cayley graph constructions or split Cayley graph, when you have normal subgroups, the cosets of the normal subgroups give you a nice equitable partition of the graph. So from equitable partitions, you get quotient matrices, and those characteristic polynomials have to divide the characteristic polynomial of the whole matrix. So, I mean, if we're not working on big enough numbers of vertices that we actually run into, like, say, a simple group or something like that. And right now we have groups with normal subgroups, and so we can use them by looking at possible quotient matrices with respect to those. You just find possible intersection. So now we have these 3 connection sets we want to find. Well, we can boil it down to 2 most of the time. We find those. Well, I mean, there's a big binomial coefficient that you have to search over. Well, one thing you can do is say, well, if this graph existed, because of this normal subgroup, there's this equitable partition. And the connection sets then have to intersect that equitable partition in a certain way. So, for example, suppose you have a group of order, I went and did a big one just for fun, but order 72, which had a normal subgroup of index 2 in it. This is a toy example. Usually you'd need a normal subgroup with an index that's bigger than that to make it actually useful. But I just wanted something simple. Well, okay, if this has a normal subgroup of index 2, then of course that's splitting the first and the second subconstituent into 2 pieces. So you end up with a 5 by 5 quotient matrix that you should get. Well, how many 5 by 5 quotient matrices are there where the numbers, I mean, so you have some thresholds on numbers because you can't have more neighbors between cells than their size. How many things like this actually have the correct characteristic polynomial? And that's one thing that's nice about the conference graphs, is that you know exactly what the characteristic polynomial of the quotient matrix has to be, because the eigenvalues are irrational, so they have to come in pairs. Whereas if you had an integral eigenvalue graph, you could have more copies of one eigenvalue than another. And so here we know exactly what the characteristic polynomial has to be. So we end up with some possible solutions that we can look for. Now, if we're just looking for S1, you might say, well, I only really need this top corner here. But you also need to know that the numbers in the top corner actually complete to some kind of quotient matrix here that actually has this characteristic polynomial. And the numbers here, maybe the eigenvalues of this look okay enough, but maybe it doesn't complete. So you have to check that sort of thing too, to narrow down the possibilities. So for example, just this turns out to be one of the things that's feasible on that number of vertices. So now, okay, we want to search for S1. We can now say, well, okay, it intersects this, the normal subgroup with 15 vertices. And well, it intersects the other coset in 20. And so now, instead of searching over all subsets, you now can look at subsets here and subsets here. You could also check interlacing if you wanted there as well, and try to narrow down the number of possibilities. So now also you can take any normal subgroup and do this with respect to that and find what the possible intersection patterns of your S1 and the cosets of this could be. And that can be very powerful to narrow down how many ways you can pick S1, quite a lot. And you really want to do that because the real bottleneck is S2. So for example, with S1 fixed, we know this intersection pattern. And now we can find different S1s. Actually, for this particular group to do this, I had used a normal subgroup of a lot bigger index. It was like 12, but for this toy example, we're just doing 2. Now, since S2 is not inverse closed, that's the real bottleneck. And Bill and I have spent a lot of time doing a lot of things with S2, trying to get that narrowed down, because that's a really tricky connection set to find. And one thing you want to do is you want to fix an S1 and use the fact that S2 has to behave nicely with respect to it. Because again, you're trying to avoid choosing 72, choose 36 different subsets, right? That's going to just be awful. So I have this vector approach that I was going to describe here as one of the ideas we implemented, but I think in the interest of time, because I think I'm supposed to stop at 1 here, I'm going to move on and say, okay, you can still use the normal subgroups of the group to try to cut down on the number of possibilities. You know the intersection sizes, but also there are other group elements that are just preserving all those cosets. And if you look at the number of common neighbors from those, actually you can they're quite controllable and easy to use. So now what did we end up finding? So first of all, for 65 vertices, we found that actually the group that Gritsenko used gives 16 non-isomorphic graphs coming in 8 complementary pairs, and that none of those complementary pairs are 2-graph switching equivalent. So there are 8 different 2 graphs that really one is getting from them, if you're familiar with that. But we also found there's another group that works. This is group G14, and this one is split. And I don't know, that just makes me more comfortable because I can write it as a semi-direct product. It's a funny group. It's kind of like a dihedral group, except instead of reflections, they're all elements of order 4. So it's kind of or actually, no, wait a minute, I'm sorry, that's G20. But well, anyway, this group is a fairly simple, easy, I should say, group to describe. And we found 4 complementary pairs of conference graphs there. All the graphs had this group of order 32 as their full automorphism group. And these, because they have just a different automorphism group, we immediately knew were not going to be isomorphic to the Gritsenko example. We also then, I mentioned how I'm letting S3 basically be the complement of S1, and that makes things nice. You can let it overlap. And redoing this, though, you don't find any other examples or groups that work. So there were 51 groups. The abelian ones don't work, and there are only 2 that do, that give you this. So it looks like if you have a lot of groups, maybe there's just a lot more chances to succeed. For 85 vertices, that is now the smallest open case for a conference graph. Unfortunately, there's only 6 groups of order 42 to iterate over. And well, after an exhaustive search, we can say actually that there are no graphs of this type, unfortunately. 2 groups came really close, though. I mean, actually, I didn't think you could come this close and not actually get there. But the intersection sizes between S1 and S2, when you do the little counts, you can make a graph, and the lambdas and mu's are the common neighbor counts. in the first subconstituent, but they're not aligned properly. Like sometimes two adjacent vertices have mu common neighbors, right? So the numbers are kind of scrambled. In one case, there were only I think 4 neighbors that were off, but that's for each vertex in the subconstituent, first subconstituent. So, but that's as close as you can get. Some other things that we found, for Q equals 61 and 89, we found some things that are not isomorphic to the Paley graph, and they have a strictly smaller automorphism group, and of course they're not 2-graph switching equivalent. And then I just have this question, were any known before? So I had asked Andries Brouwer, and he looked at the same references I did basically, and didn't see a construction, but maybe there is something known. So I don't know. I really wanted new numbers of vertices. I think that was Bill and I's big dream here. And you know, the search is still ongoing, but it's gotten a lot bigger. So now another thing that was kind of interesting is is one of the examples that was from the different group, not the Gritsenko group, but the other one that worked. For Q equals 65 has a very strange structure that it's 4 Paley 17 graphs that are all touching at a vertex. And then there's just the cyclic group of order 8 is preserving all of them simultaneously. And then there's just these new connections between them, you know, that's filling out the whole graph. Can that sort of thing be generalized? I mean, so we have in Paley graphs, other Paley graphs living inside, but they form this equitable partition. They're like all these disjoint ones. Here we have a fan of them through a single vertex. You know, that's a kind of strange. So here is some other data I collected just when Bill and I did this search of all the things that we found. I need to update it because we've gone farther than this, but actually just to give you an idea that, you know, there are different groups that can work and some different things that come up, but on some things that are non-isomorphic to the Paley graph. So for 61 and 89, the non-isomorphic things were still from the cyclic group. Interesting. So there wasn't a non-abelian group that worked there. For 117 vertices, so these are the next open cases. 117, that's a bad numerology because there's only 2 groups. So, and one of them's dihedral, which we know can't work. It has too many involutions. So the next case that looks hopeful is 145 vertices because there are 50 groups of order 72. But the problem is the combinatorial jump. I mean, it's really big. And so we're at the point we can get all the feasible S1s and S3s. The S2s, I think for some of the groups, we could get all the S2s in a month each. But I've been on the move and I haven't run anything that long, but I think that's about where the complexity is. So maybe in about 45 months or so, we could do the whole thing, but I'm hoping there's some way to cut things. Now, I guess just quickly, I'll mention that I was surprised that such a simple symmetry assumption, you know, a vertex that's fixed and then transitive on each subconstituent, yielded something on 65 vertices. Because I mean, this is the sort of thing I would have thought, since in geometry this sort of thing is done all the time, would have been known exhaustively a long time ago, but apparently not. So it makes me wonder about other things that could be tried for building strongly regular graphs. There are other parameters where, first of all, there's the valencies are half and half, so you could have this assumption that these are both Cayley graphs. Then there are also a lot of parameters of this form, where the size of the first subconstituent divides the size of the second subconstituent. And so then you can assume maybe the first subconstituent is Cayley, or no, the second subconstituent is Cayley, and the first maybe has some non-trivial stabilizer. And, you know, I mean, I'm more optimistic now. Like if I was thinking about this before Gritsenko's graph was found, I would have thought, well, somebody did that a long time ago. But now it appears not, has not been done exhaustively. And so I'm interested if maybe some things could be found along these lines. So that's an open question. Okay, and that's all I have. So thank you very much.
Vice Chancellor Giesecke.
Hi, Jason.
Hi, Emily. How are you?
Doing fine. Funny that we're normally so close, and this is how we're discussing things.
Oh, yeah.
Yeah, interesting talk, and actually related to the talk I'm going to be giving tomorrow. Like the first question that pops in my head is the equiangular type frames that are associated with these SRGs. Like, so you've come up with sort of these new SRGs with the same parameters, and I'm kind of curious now what the linear algebra properties, like the matroidal properties and linear dependencies of the associated real equiangular type frames would be with these kind of new constructions.
I see. So those are determined by the parameters then that's a little step above that.
Yeah, so it's you. Actually, if Matt is in the audience right now, I think it's from one of his papers, the showing the connection, but I think you...
Let's look at this again.